thanks for the organizers for having me. I want to also apologize in advance for misspeaking. I'm sure I will. I'm very jet lagged. I'm sorry. I want to just give you the take-home message for this paper right here in the talk today, in which we answer Boob's question, why the Tsirelson bound, according to Fuchs' desideratum, and that's down, here we go, that we take the structure of quantum theory and change it from this very overt mathematical speak into something like special relativity. And the answer is, the Tsirelson bound obtains due to conservation per note preferred reference frame. So there's no new physics here. I'm not proposing that quantum is wrong, just the opposite. I think quantum is more right than we give it credit for, perhaps. So here's the backstory. The co-authors with me on that paper were also the co-authors with me on this book, which came out at Oxford last year, in which we resolve a number of the mysteries in modern physics by using constraint-based explanation rather than dynamical explanation. Now, that'll make sense more here in a second. So Jeff Boob is just down the road from us. We're good friends with him. And he said, hey, why don't you guys come on down here and give a talk on your book? So we spent several hours there with Jeff. And at the end, he said, well, this all looks well and good, but could you just tell me what exactly is the principle, what you would call your constraint, that would explain for me, that makes sense for me, of the Tsirelson bound, right? In other words, why the world is quantum rather than classical, why the world is quantum rather than superquantum, right? Why the Tsirelson bound? I have to admit, I'm not in quantum information theory. I have fit data to the 2 root 2. I just never heard it called the Tsirelson bound. I never heard of superquantum correlation, so I had to go and look it up and see what are these guys talking about. And what I found a number of places was, when they're talking about principles, they were specifically mentioning special relativity. Can you find some kind of a principle like the light postulate where we could make sense of the Tsirelson bound? Of course, they're talking about all of the quantum, right? But this is just one specific aspect, right? Entanglement for the Tsirelson bound. And I like this as Fuchs said, if we don't do something like that, right? If we can't turn it into something like this, then the debate's going to go on forever and ever. I've been doing it for 25 years, and that seems to be pretty much the case. So here was the charge to us from Jeff. It said, tell me why we have correlations which violate the CH-SH inequality all the way to the Tsirelson bound, but no further. Because all those correlations satisfy no signaling. So that's not it, right? And we know the structure, we can derive it from this structure. So what we need is some kind of an explanation for the phenomena associated with this kind of a basis state structure. And then it should be quite clear why your superquantum correlations violate that principle. It should be crystal clear. I don't have time to show you that and all the stuff that's in the paper today. I'm just going to focus on one simple example where it's very clear the point that I'm trying to make, the take-home message, okay? So we'll look at spin. And the main differentiating feature between the classical and the quantum situations, of course, is the quantum +1, -1. You don't get fractional results, right? In fact, that's the property that uniquely characterizes the classical and differentiates the classical from the quantum joint distributions. So we'll take spin. We'll look at the spin singlet state. It's an easy one with our friends Alice and Bob, as usual. And now let's just look at the phenomenon in question. So when they have their Stern-Gerlach magnets aligned, represented by the blue arrows, their outcomes, represented by the yellow dots, are always opposite. 50-50, up, down, down, up. When their Stern-Gerlach magnets differ a tad from each other, you still get mostly different results, but now you start getting some that are the same. Your correlation went from -1, it grew, got a little bit larger. Until when they're at right angles, all the things instantiated equally, correlation 0, keep going, it keeps growing, until when they're anti-aligned, correlation 1. So this is just an empirical fact. The correlation for this situation goes as minus cosine theta, and this is correlation which is responsible for the Tsirelson bound, for the CH-SH inequality, right? So this is what we need to explain. Need some kind of a principle, a constraint, which would tell us why this is the fact, right? So let's pause right here and take stock of what we have already compared to special relativity. They kept mentioning postulates like special relativity, principles like special relativity. All right, well, let's compare the phenomena to the phenomena for the light postulate of special relativity, okay? In special relativity, we see Alice moving at velocity VA relative to a light source, and she measures the speed of light to be c. Bob moving at velocity VB relative to the same light source, and he measures the speed of light to be c. What do we mean by reference frame in this context? The reference frame here refers to the relative motion of the observer and source, which then defines a specific measurement of a specific quantity in the context of all its alternatives. So no preferred reference frame in this context means all your measurements produce the same outcome, c. As a consequence of this constraint and no preferred reference frame in general, the relativity postulate, then relativity is a constraint-based / principle theory, right? Now, let's look at what we have here for the phenomena, the Tsirelson bound phenomena, right? In quantum mechanics. Alice orients her Stern-Gerlach magnet at alpha relative to a source of spin-entangled particles, and she measures plus or minus 1. Bob orients his Stern-Gerlach magnet at beta relative to the same source of spin-entangled particles, and he measures plus or minus 1. Here, reference frame refers to the relative orientation of the Stern-Gerlach magnets and source, which then defines a specific measurement of a specific quantity in the context of all its alternatives. So, no preferred reference frame in this context means all measurements produce the same outcome, plus or minus 1. Right? Now, what we're going to see next is this means that you're only going to get conservation on average. That's what I'll show you next is the constraint. And then that constraint plus this one, again, no preferred reference frame proper, then produce the quantum state, the probability for each measurement outcome. All right, so let's look at a particular situation. For some alpha, some beta, we do all the trials, n trials, we write them down like this. This is the correlation. Now we organize them according to, say, Alice's perspective. Look at all Bob's results to go with her plus 1, all Bob's results to go with her minus 1. Since you get 50-50 plus minus, you can rewrite this expression like this. And so now saying we want some kind of a physical principle or constraint to explain the correlation, then it comes down to right here. Can you give me some reason that Bob averages what he does for Alice's plus 1 and for Alice's minus 1? This situation is symmetric, obviously. We could have set this up for Bob and making the same claim about Alice, right? So Alice would say, okay, look, my plus 1 result. Well, if you do the same measurement, you got to get minus 1, right? We know that. That's our conservation right there. So if you do some other measurement, you should get a projection, right? Minus cosine theta. I mean, this is classical reasoning. That's precisely what's not true in the quantum situation, but that's what we want to explore, right? So you're supposed to, she would say to Bob, you're supposed to be getting something like negative 0.3 or positive 0.5, right? Not plus or minus 1. But again, no preferred reference frame. Bob only obtains plus or minus 1. So let's posit as our constraint, our principle, that Bob will average the required minus cosine theta, right? So what does this look like when you look at averages? Alice says, okay, let's look at your averages for my plus 1s, right? See, your average makes perfect sense. See how it's just a projection onto your measurement direction. Makes perfect sense. Likewise, for the minus 1 results, you got to average positive cosine theta. You stick those in, get your quantum correlation. So that's just a mathematical fact. Now, whether you believe that that's a real constraint or not, that's just a mathematical fact, right? You put those averages in like that. Now, in the paper, of course, we go to Hilbert space and show that in general, whatever the theta represents, it will generalize to whatever conservation of whatever binary information the outcomes, yes, no, up, down, on, off represent. Okay, so let's look at what we have. Just as the light postulate of special relativity follows from no preferred reference frame, the quantum correlation function, whence the Tsirelson bound, also follows from no preferred reference frame. Alice and Bob each measure plus or minus 1 equal frequency for any measurement, They confirm conservation of binary information when they're doing the same measurement, they're in the same frame. And then the other, right, either can argue that the other averages what they should have got. When I got this +1, you got -1 or +1 for that. You should have got -0.3 for that. You got to average all yours, Bob, right? All right, but Bob can say the same thing about Alice. No, my +1 and -1s, right? Yours should be averaged. All right, so on a trial-by-trial basis, what does this constraint get us? Nothing. Absolutely nothing. Why this particular outcome? What does the constraint tell us about this particular outcome? Absolutely nothing. Trial after trial, equally mysterious on a trial-by-trial basis. It's only when you look at the collection of trials that your constraint is applicable. The constraint explains outcomes only as a whole. This is conservation for no preferred reference frame. So, presented this to dozens of physicists over the past year. They all agree. Well, yeah, duh, of course. I mean, it follows as a mathematical fact, for one. But two, yeah, I would think that that's probably true about the data itself, that it does satisfy this constraint as a matter of it being a constraint, sure. But the problem is, what does it explain? You have this conservation principle with no compelling dynamical counterpart. And typically, adynamical constraints have a dynamical counterpart, right? Conservation of momentum. Some of the forces are zero. Fermat's principle of least time. Snell's law of refraction. You see how this is, again, just like the light postulate? Everyone measures the same speed of light. Why? Well, no preferred reference frame. All right. Well, what makes that happen? What dynamical mechanism enforces that constraint? Nope. And that leads to a mystery of special relativity, right? So, again, we have, this is Alice saying of Bob, you should average your results. Then it makes sense. Bob says of Alice, no, you should average your results. It makes sense. So now let me juxtapose this with what we know from special relativity to bring home what underwrites both, right? This is an example from DeWitt Merman. I adapted it by adding an event so things are all local. You don't have to worry about light delay, time delay with light. And also I exaggerated the time differences to make it more fun. This is in our book. So what we have here are two sets of observers, the girls and the boys, and they agree on all the facts here. They're related by Lorentz transformation, which comes from the fact that they all have to measure the same speed of light, right? Don't worry about remembering that. You'll see it in the diagram. Okay? So let's look at this. Event 1 and Event 2. Well, the boys say Event 1 and Event 2 happened at the same time. Why? They're twins. They're the same age. They're both 20 years old. So Bob kissed Kim when he was 20, and Joe kissed Sarah when he was 20. Sarah was 20, Kim 17 and a half. And the girls say the distance between them here is 1,250 kilometers. The boys say, no, the distance is only 1,000 kilometers. Your meter sticks are too short, see? What do the girls say? No, dude. Our meter sticks aren't short. Your meter sticks are short. And those events, 1 and 2 didn't happen at the same time. 1 and 3 happened at the same time. We're all the same age. We're triplets. We were 20. Sarah says, when I was 20, Alice was 20. 20-year-old Alice is kissing 22-year-old Bob. When Sarah, 20, kisses Joe, 20. The boys say this distance, right, is 1,000 kilometers. The girls say, no, it's only 800. Your meter sticks are short. And 2.5 years elapsed between the time of events 2 and 3, when Bob kissed Kim and Bob kissed Alice. The girls aged 2.5 years. Look, Bob only aged 2 years. Your clocks are running slow, too. And, of course, one more event to flip that, right? Bob's 25.6, kisses Sarah 24.5. Sarah only aged 4.5 years between the time she kissed Joe and Bob, where the boys aged 5.6 years. So now the boys say, your clocks are running slow. See? That's the relativity of simultaneity. That's what makes special relativity so weird, doesn't it? Because, look, if you really believe no preferred reference frame, then the boys really are the same age, and they're not the same age. And the girls really are the same age, and they're not the same age. And where does it come from? Where does that fact come from? The fact that they have to measure the same speed of light. All that follows from the fact that they have to measure the same speed of light. All that weirdness. And now let's just put it side by side. Okay, so special relativity. Empirical fact. Alice and Bob both measure c regardless of their relative motion. Quantum mechanics. Empirical fact. Alice and Bob both measure plus or minus 1, again, and this is h bar over 2 units, regardless of their relative SG orientation. Consequence. Over here. Well, the consequence of this empirical fact is Alice says of Bob, your clocks are running slow and your meter sticks are short. And Bob says, no. Bob says about, it's your meter sticks that are short. Your clocks run slow. What happens over here is a consequence of this empirical fact. Alice says of Bob, you're measuring the wrong things. When I got +1, you should have gotten -0.3 and or +5, or you know what I'm saying? And then what does Bob say? No, no, no. My +1 and -1s are right. You got to average your results to get the right answer. No preferred reference frame. Implication? What we find so weird about special relativity. The boys are the same age and they're not the same age. If you're really going to buy into that, there's no real preferred frame. That's a fact. And over here, what weirdness obtains in quantum mechanics as a result of this fact? You have average-only conservation. You don't have on a trial, but you have a conservation principle for the data itself. No hidden variables. Nothing under, these aren't representative of some other value for the angular momentum that was not measured. No, this is a conservation principle that obtains for the value, the data itself, right? And so, it only obtains on average. Trial by trial, nothing to say about that. Okay, you can again choose not to buy into that because of the weirdness, and so you start trying to generate over here something about an ether, mechanical mechanisms that actually makes clocks run slow. Over here, you might propose that there really are hidden values for an underlying value of the momentum that's projecting on what they get on each trial, or you have some superluminal causal mechanism which conspiring to make you get this, right, to get the right probability outcomes. Or you can simply accept the fact that the constraint is true. Just because we find that it's weird doesn't mean it's wrong. All right. Now in the paper we show how the, sorry, don't have time for that. That's showing explicitly how the PR correlations violate that. Okay, so here's our answer. Again, for Boob, he said, for him, why the quantum, right? Why the world is quantum instead of classical and quantum instead of superquantum? For him, he says that reduces to why the Tsirelson bound. Why do we have the Tsirelson bound? Because conservation for no preferred reference frame, exactly as those in QIT were asking for, right? Fuchs desideratum. Okay, Fuchs quotes Wheeler. If one really understood the central point and its necessity in the construction of the world, one ought to state it in one clear, simple sentence. Asked if he had such a sentence, Fuchs responded, no, that's my big failure at this point. Thus, the one clear, simple sentence explaining the central point and its necessity in the construction of the world and answering Boob's question per Fuchs desideratum is the Tsirelson bound obtains because of conservation per no preferred reference frame. Right? Now, again, that's just a mathematical fact. Whether you believe that this constraint is somehow really responsible or really true, I'm just pointing out mathematical facts that follow from the empirical facts, right? So, and then, again, no preferred reference frame means you only get plus or minus 1 outcomes. And from that, means you can only satisfy your conservation principle for the data proper on average, which then gives you the QM correlation when it's the Tsirelson bound. So we have a constraint-based / principal explanation of the Tsirelson bound, just as in special relativity, very much like in special relativity, right? Which that's what they were asking. I mean, that's what Boob asked me. Can you give me something like that? I would say this is very much like that, yes. So Smolin recently said in April, talking about his new book, he said in his video presentation, quantum mechanics doesn't make sense because it's wrong. So I'm proud to stand here and say that to you today, the same stage where Penrose said this recently here at Perimeter. Our response to that is, no, no, no. Quantum mechanics isn't wrong. It's very right. Quantum mechanics makes perfect sense. And it's entirely consistent with relativity if you look at both as a product. How much time do I have?
It's fine.
Good.
2 minutes.
Okay, good, because that's my last slide. So, quantum mechanics is not wrong. Far from being wrong, it makes perfect sense. You look at it in conjunction like this, no preferred reference frame. But what you have to be willing to do, and this is the whole point of our book. Our entire book is written about weirdnesses, problems like the flatness problem, grandfather paradox from general relativity, origin of the universe, things like that from general relativity. And then you have oodles, of course, besides this one from quantum mechanics. And we show that they all result from requiring or expecting dynamical explanation. If you accept your constraint explanation as sufficient to explain it, then you're done. It's fine. There's nothing wrong. That's the point. That's the take-home message. Thank you.